we have this infinite product 2 over square root of 2 times 2 over the square root of 2 plus square root of 2. Here's the pattern. So just copy it down this denominator, square root of 2, and add on 2 to it. Take the square root. And copy it down this whole denominator. Put it down here. Add a 2 onto it. Then take the square root of everything. So here's our infinite product. Then we're going to use this trig identity and those double angle formulas to help us prove this, to solve for this. So first of all, the fact that we have 2, so the reciprocal is half of square root of something. That reminds me of double angle formula. Cosine x equal to half of cosine 2x plus 1. Take the square root, derived from this double angle, when x is in first and fourth quadrant. And we're going to also use, and so further, this double angle formula further motivates us to use this trig identity. So also going to use this double angle. So first of all, I'm going to denote the finite product f sub n of x equal to cosine half x times cosine x over 4 times cosine x over 8 all the way up to cosine x over 2 to the power of n. That's the pattern. The denominator just doubles every time. So here's my finite product, denoted as f sub n of x. Later we're going to let n approach infinity. Now I'm going to multiply everything, multiply by both sides by sine of x over 2 to the power of n. Times f sub n of x is now equal to cosine half x cosine x over 4 cosine x over 8 all the way up to cosine and sine x, and so here. So now I can apply the double angle formula. This sine cosine equals half of sine double angle. So what's the double angle of this angle? What's the double? X over 2 to the power of n minus 1. That's the double angle. So here, I can just replace those two terms with just half of sine of x over 2 to the power of n minus 1. Right? And so there is a term prior to this term. What's that term? There was also some cosine. And that should be cosine x over to 2 to the power of n minus 1. Right? That's the term prior to this term. So again, I can repetitively use the double angle formula. So this is in fact half of sine of double this angle. That is x to the power of 2 to the power of n minus 2. So this whole thing can be replaced by 1 over 4, half. So 1 over 2 to the power of 2 times sine x over 2 to the power of n minus 2. And we can just repetitively use the double angle formula. So what's the pattern here? What's the pattern here? So eventually, as we move on, continually apply it, all the cosines will be gone, right? So this will be gone, this will be gone, simplified, all combined into some double angle. So in the end, we're only gonna be left the first term. Then we'll simplify that also later. So here, there was another previous term which was cosine of x to over 2 to the power of n minus 2. That was another previous term. So imagine if so eventually the power will just keep reducing and reducing. But the power of this term will keep increasing and increasing. And their index, n minus 2 and 2, they add up to n, always add up to n. So that's the pattern here. So eventually I'm guessing this power down here will reduce all the way down to just cosine of x over 2 and times 1 over 2 to the power of, because remember, their index always add up to n, so 2 to the power of 1, so 2 to the power of n minus 1 times sine x over 2. So eventually I have this. So cosine x over 2 is exactly my first term. So in other words, in this case, this will be gone, this will be gone, right? All I have left is this on the right-hand side. So again, for the last time, we applied double angle formula. This times that equals half times double angle and times this term. So that will be equal to 1 over 2 to the power of just n and sine double angle x. So this is actually equal to left-hand side. So in this case, we're gonna divide everything by sine x to the power of 2 to the power of n. So in other words, now f sub n of x should now equal to so 1 over 2 to the power of n times sine x, that's on the numerator. What's on the denominator is this term, sine of just x over 2 to the power of n. And that's the so again, we're gonna remember the well-known limit. Limit as x approaches 0 of just sine x over x is equal to 1, which I will perhaps also prove it in a future video in a number of different ways. But this is a famous limit. Now, in this case, I don't exactly have x. I just have x over 2 to the power of n. I'm going to somehow make it up to make it whole. For example, I'm going to multiply both the top and bottom just by x. Right? So here I multiply by x. So x appear up here, and there, x at the bottom. Now, look at this. X over 2 to the power of n as a whole thing. X over 2 to the power of n also as a whole thing. Right? Now I have exactly the same object inside of the sine and here at the top. So in fact, the reciprocal is always approaching, also approaching to 1 as well. So this is like the reciprocal, except this inside here I have, instead of having x, I just have x over 2 to the power n as a whole identity. So here. So in fact, this over that approaches 1, right? So this over that approaches 1. And I'm still left with sine x over x. So this should approach just sine x over x as n approaches infinity. As n approaches infinity. Because sine over 2 to the power of n approaches 0. as n approaches infinity, obviously. So here x approaches 0, no problem. This is legitimate. This is when x is not equal to 0. So we've proven this identity. Now I've proven this trig identity. So I'm going to solve this infinite product. I'm going to let x equal to half pi. So x equal to half pi. So in this case, I can work out cosine pi over 4. Cosine pi over 4, of course, is easily half of square root of 2, as we know, this famous trig. So what's cosine? It's half of its angle. Cosine pi over 8. Using this identity we've derived from this double angle formula. So here x is really in the here my angle is really in the first and fourth quadrant. First quadrant, so it's positive square root. So square root of just half of 1 plus this trig value. And we can simplify it, in fact. So after we use the common denominator of 2, right, on the top, and we have to divide by 2. So we have 4 at the bottom. So square root 4 is easily just 2. And we still have square root on the top. That is 2 plus square root of 2. Right, so we just common denominator, so 2 over 2. 2 plus square root of 2 over 2. And 4 at the bottom, so it's 2. So here's my simplified version. What's cosine pi over 16? Again, the 2 half of just 1 plus this. So half of square root of 2 plus square root of 2. Let's square everything. This is equal to, again, this time we will multiply everything by square root of 2. Both top and bottom. So bottom we have square root of 2 after I distribute the square to both top and bottom. So square root of 2 times square root of 2. Bottom I now have 2. Top I have square root of this whole thing times another square root of 2. So I can just combine the square root all together and multiply 2 to the inside. So still I have square root. Inside I have 2 times this whole thing. That is 2 plus 2 and 2 simplify, cancel out. I have square root of 2. I have a square root this inside expression, 2 plus square root of 2. Right. So this is already, the reciprocal of this term. This is the reciprocal of this term. And this is the reciprocal of this term. So this infinite product is in fact the reciprocal of the product of this infinite product. That is, my infinite sum is equal to 1 over cosine pi over 4 times cosine pi over 8 times cosine pi over 16, all the way up to infinity. This is equal to, like I said, this time I let x equal to half pi. All right, so x equal to half pi. So this becomes cosine pi over 4 times cosine pi over 8 times cosine pi over 16, all the way equal to this when x is equal to half pi. So in fact, this is in fact equal to 1 over sine half pi over half pi. Right, when x is equal to half pi, replace x with half pi. This reciprocal. So sine half pi is equal to 1. So 1 over the reciprocal of pi over 2, that is pi over 2. That's the final answer.